Hello everyone. Today we will talk about isomerism in carbohydrates. Carbohydrates show isomerism, which means they can exist in different form called isomers. So what are isomers? Isomers are two or more different compounds having the same molecular formula, but either they have different structure or they have different 3D arrangement of atoms, and because of that they have different chemical or physical properties. So there are two types of isomers in carbohydrate: structural isomers and stereoisomers. Stereoisomers are further classified as enantiomer, which are mirror image to each other, and diastereomers, which are not mirror images. Dual isomers are type of enantiomers, and epimers and anomers are diastereomers. Let's first talk about structural isomers. What are structural isomers? They have same molecular formula but different connectivity of atoms. So let's understand this with example of glucose and fructose. Glucose and fructose have same molecular formula of C6H12O6, but they are different because glucose has aldehyde as carbonyl carbon, whereas fructose has ketone as carbonyl carbon. So because it is aldehyde, it is one sided attached with hydrogen and one side with this R group, and since it is a ketone, it is attached both side with R group, this side this CH2OH and here this R group. That's why they have different structure and they are structural isomers. They have different properties too. So glucose is main sugar present in our blood, and fructose is major sugar present in fruits. Fructose is sweetest natural occurring sugar, and both glucose and fructose have different metabolism. Glucose is metabolized in almost every cells, while fructose is mainly metabolized in liver. Next one are stereoisomers. Stereoisomers have same molecular formula, they have same structure, but they have different arrangement of atoms. So let's talk about the first stereoisomers, that is DL isomers. They are enantiomers. Let's understand this with example of glyceraldehyde. So stereoisomers have the chiral carbon. They should have at least one or more than one chiral carbon. So first let's understand what is chiral carbon. So look, chiral carbon are carbon which are attached with four different groups. If you look at this carbon, this is attached with only three groups: oxygen this side, hydrogen this side, and this group. If you look at second carbon, it is attached with four different group: aldehyde here, alcohol here, here this OH group here, this H group here, and here this is CH2OH. So this carbon number 2 is attached with four different groups. It means it is chiral carbon. If you look at third carbon, it is attached with two hydrogen atoms, means it is not attached with four different groups. So only second number carbon is chiral carbon. Because it has this chiral carbon, its mirror image is not superimposable to each other. If you look here, this OH is on right side, here it is on left side in mirror image, and here hydrogen here, left side hydrogen here, here hydroxyl group, right side of hydroxyl group here, hydrogen here. So they are not superimposable to each other. Since their mirror image are not superimposable on each other, they are called as enantiomers. And because of this chiral carbon, different position of this OH, they are two different isomers. They are isomers. So if on this chiral carbon, if this OH on the right side, this is called D sugar. If this OH on the left side, this is called L sugar. So this is D glyceraldehyde and this is L glyceraldehyde. Now let's talk about dihydroxyacetone. This is also a 3 carbon sugar. If you look at its first carbon, it is attached with two similar groups, that is hydrogen. Similarly, this third carbon is also attached with two similar hydrogen groups. If you look at second carbon, it is attached with two similar groups, CH2OH here and CH2OH here. So none of these three carbons are chiral carbon. So dihydroxyacetone does not have any isomer. Except dihydroxyacetone, all monosaccharide have their stereoisomers or enantiomers, because it does not have any chiral carbon. So what are DL isomers? This is the property of chiral carbon. They form non-superimposable mirror image and they are known as enantiomers. It is configurational rotational system. Why configuration? Because they are isomers because of position of this OH, configuration of this OH, whether it's present in right direction or in left direction. We can calculate the number of stereo isomers by using this formula of 2 to the power n, where n is the number of chiral center. So if you want to calculate the number of stereoisomers of this glyceraldehyde, here it has only one chiral carbon. So if you use this formula 2 to the power n, you will get the value 2. So glyceraldehyde has only two of these isomers. One is D-glyceraldehyde and another is L-glyceraldehyde. That way you can calculate the number of stereoisomers for all sugar by just knowing how many chiral carbon they have. Let's understand this with more example. So this is the 4 carbon sugar, had the molecular formula of C4H8O4. So if you look at the chiral carbon, it has 2 chiral carbon, this second number and this third number. So now confusion is, which carbon should I look for to name them, where they are D sugar or L sugar. So always remember that for that we always look at the farthest chiral carbon, which is farthest from this aldehyde group. So here you look at, if you look here, this third number carbon is farthest from this aldehyde group. This second is closer, so we will always take this farthest carbon, and this farthest carbon is called as penultimate carbon. And why are we taking this? Because this carbon corresponds to that single chiral carbon present in glyceraldehyde. So to keep the uniformity of this isomerization, we always take the this penultimate carbon to name them D and L sugar. So here on this penultimate carbon, if OH on the right side, they will call as D sugar, and if OH on the left side, it will be L sugar. Likewise, here we will see another stereoisomers of this erythrose. So if you are changing the position, just configuration of this OH at carbon number 2, you will get another sugar. So this is threose. Here both the OH on right side, so this is erythrose. Here one OH is on right, on one on left, so this sugar. So by changing just position of H and OH, it's completely the different sugar. So on penultimate carbon, this OH is on the right side, so this is D3Os. This OH on the left side, then this is L3Os. One thing always remember, D-erythrose and D3Os are stereoisomers, because why they are isomers? Because of just change in position of this OH and H. That's why they are stereoisomers. But D-erythrose and D3Os are not enantiomer, because they are not the mirror image. So D and L type of sugars are enantiomers, but all these are stereoisomers. Likewise, D3Os and L3Os are enantiomers, and they forming the non-superimposable mirror image. So you can calculate number of stereoisomers formed by this 4 carbon sugar. Since it has 2 chiral center, you use the formula 2 to the power 2, you will get the value of 4. So 50% will be, whatever value you get, the number of stereoisomers, 50% will be of D form, like D-erythrose and D3Os, and 50% will be of L form, like L-erythrose and L3Os. Likewise, you can calculate for like glucose. Glucose, this is the 6 carbon sugar. There are 4 chiral centers at second, third, fourth and fifth carbon number. So you can use this formula 2 to the power 4. You will get total 16 stereoisomers. Out of 16, 8 will be of D sugar and L will be of L sugar. So we learn 3 terms. Stereoisomers, if they have only different orientation of atom like H and OH. Enantiomers when they form non-superimposable mirror images, and DL isomers because their position of this OH on penultimate carbon, whether it's on right side, if it's on right side they will be D sugar, if it's on the left side they will be L sugar. Next one are optical isomers. Optical isomers is property of enantiomers, means DL sugar are also the optical isomers. DL sugar have the property to rotate the plane polarized light. That's why they are called as optical isomers. Optical means light. Since they are rotating the light, they are optical isomers. Only not rotating the light, actually these isomers are rotating the light differently. That's why they are isomers. So let's first understand about that. What is plane polarized light? So normal light vibrate in all direction, but when you pass this light through polarizer, it's convert the vibration of light in only one it allow to pass the light which vibrates in only one direction, and this light is called plane polarized light. Now if you pass this plane polarized light through sugar solution, this sugar solution will rotate this plane polarized light either toward right, or you can say clockwise direction, or toward left, that means anti-clockwise direction. So if this sugar solution rotate this light toward right, they are called as dextrorotatory, and it is denoted with a small, either a small d sign or plus sign. And if this sugar rotate this light toward left, they are called as levorotatory, and it is denoted with either a small l or minus sign. So when we do this experiment, we get the value of optical rotation, and that is called as alpha observed, and this alpha observed depend on length of this tube in which sugar solution is kept and concentration of the sugar. So whenever you change the length of tube or if you decrease or increase the concentration of sugar, you will always get the different value of alpha observed. So we always calculate the specific rotation. So this is the formula of specific rotation. So to calculate the specific rotation, optical rotation, we use this formula of alpha observed divided by length into the concentration. So length is measured, this length, tube of length is in decimeter, and this is the concentration in concentration of the sugar in gram per ml, and we always measure it at a specific wavelength and temperature. So if you want to calculate the optical rotation of 1 gram of glucose which is dissolved in 1 gram of water and measured in 1 decimeter of tube, it will, if you it gives the rotation of plus 5.2, means you have got the value of this alpha observed is plus 5.2. Then you can calculate the specific rotation per unit length of the tube and per unit concentration of the sugar by just dividing this using this formula, plus 52 by 1 into 1. 1 is this concentration of sugar and this. So finally you will get the value of this 52 degree, which means it this sugar is rotating the light in right direction because it's positive, it's rotating this way and at the angle of 52 degree. Now you always remember that these two isomers, enantiomers, D glucose and L glucose, rotate the rotate the plane polarized light, but always in opposite direction. If D is rotating the light in right direction, L will rotate the light in left direction. So example is D glucose rotate the light in right direction, means it is dextrorotatory, while D fructose rotate the light in left direction, means it is levorotatory. So D glucose is sometime also referred as dextrose. One more term you need to know is racemic mixture. if you are taking the 50 is to 50 or 1 is to 1 ratio of both D and L sugar, then they will be optically inactive. Why? Because if you have, suppose you have taken the 50 molecule of D glucose and 50 molecule of L glucose. So if D glucose is rotating this light in right direction and L glucose is rotating this light in left direction, then they will cancel each other's effect. So finally you will get no optical rotation. That's why racemic mixture means equal ratio of D and L sugar will be always optically inactive. Ideally they are not optically inactive, they are just cancelling each other's rotation. Next one are, we learned about enantiomers. Now we will learn about the diastereomers. In diastereomers we will first read about this epimers. What are epimers? They are isomers which have different orientation of H and OH group on single carbon atom. So here you always be specific about the term. Enantiomers were mirror image to each other, but diastereomers are not mirror image. They are also the isomers, but stereoisomers, but they are not the mirror image. If you look here, they are stereoisomers because they have different orientation of group, like this OH is on the right side and here OH is on the left side. They are diastereomers because they are not mirror image. If you look here, this OH here, OH here, but here H, if they were mirror image, here should have been OH, not H. So they are not mirror image. So that's why they are diastereomers. And why they are epimers? Because they are different, their orientation are different at only single position, only here at second number position. Since their orientation of H and OH are different at this second number carbon, so they are called C2 epimers. So glucose and mannose have the same molecular formula of C6H12O6, but they are C2 epimers. Similarly, D-glucose and D-galactose have the same molecular formula of C6H12O6, but they have different orientation of this OH and H at this 4 number carbon, so they are C4 epimers. If you look here, they are not mirror image, that's why they are diastereomers, and they are different at only this position, so they are C4 epimers. Apart from that, they are exactly same, aldehyde group here, HOH here, OHH here, so that way epimers, they are epimers. Next one are alpha and beta anomers. They are also diastereomers, means they are not mirror image. Alpha beta anomers are actually in cyclic form of sugar. So when open sugar, this is the example of glucose, are cyclized when this alcohol reacts with aldehyde to form hemiacetal. So we always get two different sugar. Why? Because this aldehyde, this carbonyl carbon, this is sp2 hybridides. So when this OH attack this carbon, this can attack it from two ways. If it is attacking this way, this will shift this OH, newly formed OH, toward downward direction. So this is alpha, this will form alpha D glucose. If this OH attack this carbon this way, it will shift this newly formed OH toward this upward direction. So this is beta D glucose. Now one thing you always keep in mind that when this glucose was in open chain structure, it has only 4 chiral carbon at second, third, fourth and fifth position. But if you look at its cyclic structure, now this first carbon, this O is now converted to OH. So now this first carbon has also become the chiral carbon, because here 4 different groups are attached now. This hydrogen, this OH, this OR group, and here this different R group. So now this has become a chiral carbon, and this carbon is now called as anomeric carbon. This is different because this is derived from this carbonyl carbon. So it has named anomeric carbon, and these two isomers are called alpha and beta anomers. You can say, look it this way as well. This OH is trans to this CH2OH, and here in beta form this OH is cis to this CH2OH. So these are two alpha and beta isomers. Now one more term you need to know is mutarotation. So when we dissolve the pure form of sugar, like here I am taking the example of D-glucose. So whenever we dissolve the pure alpha D-glucose or pure beta D-glucose, they will start interconverting, and they will interconvert until they reach the equilibrium. So at equilibrium, 63.6% will be of beta form of glucose, and 36.4% will be of alpha form of glucose, and less than 1% of the glucose will be in open form. So this conversion of one sugar to another form, like alpha, first it, if you dissolve this pure alpha, it will first open up and then convert it to beta. This beta will open up and interconvert it to alpha. This interconversion is called the mutarotation. So how it is, it can be measured. So when you take the pure alpha D glucose, its optical it rotates the plane polarized light to 112.2 degree. Pure beta D glucose rotate the plane polarized light to plus 18.7 degree. At equilibrium, when we have 63.6% of beta anomer and 36.4% of alpha anomer, that equilibrium mixture will rotate plane polarized light to plus 52.7 degree. So that was all about mutarotation. These are few questions for you. Thanks for watching. See you in the next video.